My name's Keith Klimchuk. I'm with the Environment Group at TEC. Always a pleasure to present on our fugitive dust program. I've been involved since 2016 in the program, leading probably since 2017, 2018. And it's always a pleasure to share some of the work that we're doing and progress that we're making. Of course, the importance of it is reducing metal emissions to the community. Our focus is fugitive dust because our trending shows that the reductions we make on fugitive dust, the dust that escapes our site, it's working in terms of lowering emissions in the community. And as we just learned, it's also working in terms of lowering children's blood lead levels. So that's why we continue doing what we do, and it keeps working. So just what I'm going to talk about, a little bit of background. So frame of reference, what is fugitive dust? Always good to have that clear before we start talking about specifics. The progress to date, we've got a nice trend graph in there that shows from 2012 to current, the progress that we've been making in terms of lowering fugitive dust and specifically lead. And then going to some of the current fugitive dust reduction initiatives. So we have a large program. This is just a snapshot from that program, just some highlights, but something that we'd like to share in terms of points of interest and also some of the achievements that we've made. So what is fugitive dust? We introduce this slide every time because it's good to be talking about the same language as we go forward. It's dust that escapes our site. So it's not what you see coming out of our stacks. This is specifically dust that escapes from open areas. And that specifically is what we call our triangle area. We've got a residue material that's stored there, and you see an excavator working on that. So, if we have winds pick up, dust can be lifted off of that pile as equipment moves around and it gets worked under the tires, etc. It can become friable and it can escape through wind currents that come. We also have emissions that come from buildings, so that can escape our site as well. This is in our lead operations area, and what we do is we unload lead concentrates in that building. So these trucks that are one that's coming out here, it dumps lead concentrate material in that building. There's an opening on the north side and the south side, so a wind stream can come through. If it's dusty, that wind can carry the dust out of that building, and that's how it would escape our site. And then third, we're looking at road dust. So we move a lot of material around site. It gets caught on wheels. We track it around. As you drive over top of it continuously, it grinds, it gets smaller. The interaction of the wheel with the road kicks up the dust, wind picks up, and that can carry it off site as well. So that's specifically what we're looking at in terms of fugitive dust. That's where a lot of our efforts are. Not to say that we don't have efforts on what comes out of our stacks. We do. We have a lot of efforts there as well, but we're focusing dominantly on fugitive dust because of the connection with that and metal emissions in the community, specifically lead, and also what we've seen in trending for children's blood lead. So this is progress to date, and I've got a trend here, I've got a graph. What you see in blue, this is what we call total suspended particulate. It's fine material and it's coarse material, and it's specifically the lead content in it. So that's what we have in blue going from 2012 to current. We collect that as what we call 24-hour composite samples. So we sample over a 24-hour period, and we do it every second day throughout a calendar year. So 156 samples per year. And then what we show here is the trend from 2012 to current. And of course, you can see some of the highs and then how the magnitude of those concentrations has come down. So the left vertical axis is those concentrations for lead. We measure it in micrograms per cubic meter. The black dashed line is our annual average. So you can see the annual average keeps going down. Those are the improvements that we put in place for reducing fugitive lead emissions. And we can see that in terms of the trending. So complementary to that, we've got children's blood lead results. It's an annual measurement, but just to line up in terms of the calendar year, we've spaced it across for that year, knowing that we only measure in September, not all year long, but we do that annually. We have the axis on the right side, that's the geomean blood lead concentration in micrograms per deciliter, and you can see the similar trend. So that's how we know that our work to reduce fugitive dust is what we need to do, because we see it both in terms of metal emissions in the community, as well as children's blood lead levels dropping. So looking at our current fugitive dust reduction initiatives, I'm going to talk specifically about wind controls. I had talked about it last year in terms of some of the studies that we're doing. So I wanted to show progression, what we've done over the year and what those next steps look like. Also on-site material movement review. So this is something a little bit different. We're using some of the science that's used in estimating emissions, specifically road dust emissions, and how that science can be used to re-inform how we move materials on site. And then finally, a new monitoring station. Monitoring is the key to our efforts to reduce fugitive dust, whether it's monitoring on site for sources and monitoring at our community monitoring stations to show effect. So having monitoring stations that are sited in the best area, getting the best data in terms of what we are measuring, really important in terms of what builds into our program, having that effective data. Wind controls, engineering and studies. So last year we talked about our lead unloading area. So in this particular building, we unload rail cars. So these rail cars come into this building, the lids are lifted off, and there's an excavator in that building that digs out those rail cars, dumps the material through a screen, it goes on conveyors into collection bins. An opening on the north side, the south side, and the east side. So you have opportunity for wind flows to go through. So what we looked at is option identification. We looked at all sorts of different options within that building, whether it be a bag house to collect dust, whether it be cladding on openings, all sorts of different options and costing associated with those options. And then we rank and we come up with the best option to move forward. So the best option to move forward was to restrict some of those openings and therefore the volume of air that would come through. So some restrictions where we can, openings at the north, south, as well as a barn door on the east. And restricting those airflows just diminishes how much dust will leave that building. So this has gone through engineering and project development. It's in the planning stage now. Similarly, zinc concentrate unloading. So we have another area where we unload zinc concentrates. That does not come without lead, 5% lead in zinc concentrates. So it's still a source of lead. We similarly looked at, we can put cladding and we can restrict the airflow through those locations. This would be a north-south type of opening where we see those as the dominant wind directions that we have across site. So we looked at that, but we also looked at a lot of other options. And what we came up with when we looked at the options and costing is important first step before we look at cladding was to look at generally the track out and removal of material. So we dump rail cars and we dump trucks, and it goes through a screen into holding bins below that get conveyed to their proper destination. And you can see we've had a lot of buildup on those screens. And that buildup gets tracked out and it gets tracked over multiple areas. And being spread around like that and wheels kicking it up and airflows coming through, that becomes a dominant source of fugitive dust due to this particular operation. So first step for us is to look at improving how we can collect that material and not have it left on top and tracked out. So we've got a lot of engineering work. This is in the engineering development stage, where we're looking at options to potentially raise that grading, put vibration mechanisms on it, etc., in order to better collect and minimize what tracks out. So we've talked about wind controls using wind fencing before. In 2018, we installed a wind fence at our roaster feed handling area. What a wind fence does, it has a certain amount of porosity, and through all of the frictional effects of wind coming through, it loses its power. Once it loses its power, its strength to pick up material and carry it off site becomes lower. So that's why we put in wind fencing, and you'll see highlighted in blue, we had an opening to the north. That opening was blocked by storage piles to the north. So that was thought as being a natural barrier to the wind that was coming from the north direction. Since that time, we put sensors inside and outside of the fence, wind sensors, also a wind sensor into the opening. And what we've shown is that wind travels over the storage piles. It comes at a pretty good speed into that handling area. So therefore, we have a project that's in planning stages to add those remaining panels at the north side. But in addition to that, we modeled the wind fence. We did something that's called a computational fluid dynamic model. So we have that contracted out to these experts that do this kind of thing, and they model how wind interacts with all sorts of surfaces and boundaries, etc. And that includes dust sources, and they model how it picks that material up and moves it. And they were able to give us an estimate for the efficiency of that fencing. So we can get 50% reduction in the lead that's carried out of that area based on putting this fencing in versus not having any at all. So having that in hand, we decided to extend that approach to all over site. Let's look at putting fencing in other key locations and develop a solution for site. So we took a very small model that we had done to establish the effectiveness of the fencing, and we built a model for our entire site. So therefore, we had to define all of the buildings, all of the structures that we have on site, all of the dust sources that could contribute to dust from site. And in addition to that, look at multiple locations where conceivably we could put fencing. And when you think about all of the information that went into this, this was run at a supercomputer in Japan because the computing time and power was extreme in order to generate results for this type of modeling. And if we go to the next slide, I'll show you one scenario. So what this is called is a heat map. It's a heat map for lead concentration. So when you look at the scale that's on the left here, when you look at dark blue, that's next to no lead. And as you move up and you see red, that's where you have your highest lead concentrations. So the boundaries we had looked at in the previous slide, all of our buildings, etc., those are identified on here. And then when you look at the heat map, you can see the dominant red zone. That's at our roaster feed handling location that we had looked at previously. That's with the opening to the north and the fencing around the other sides. So according to the model, that's still a significant contribution of lead. And then how it gets dispersed in terms of travel either on or off site, you can see in terms of the plume that's coming out of here. So the color changes because of course the concentration gets lower and you can see some directionality. And in this particular scenario, it was a dominantly northwesterly wind flow. So we have a dominant northwesterly wind flow and a southeasterly wind flow that follows the Columbia River. That's what we see as our dominant wind directions. So we looked at that scenario, and of course, northwesterly wind flow means it's going towards downtown trail. And then just some information in terms of speed and stability class. This came out of dominant wind scenarios that the modelers had discovered and therefore looked at in terms of further modeling for how the lead is moved off-site. So stability D just means it doesn't have much buoyancy. It goes horizontally, fairly low wind speed, but that was a dominant wind scenario. Base case, just with our roaster wind fence, opening to the north looks like this. And then multiple fences put into the model looks like this. So we closed off the north section, obviously, on our roaster pad. Some other fencing at material handling locations, strategically positioned. And you can see how we have lead basically localized to site. So something that was really useful in terms of those modeling results. Of course, validation to follow. Every model informs. How good it informs depends on the quality of data you provide to that model. Always your next step is to validate and go out and monitor different locations to prove it. So here's something kind of interesting. This is where we're using some of the science behind material movement. So companies, whether they're mining, smelter, refining, globally use these methods to do what's called metal source accounting. So what we do is we develop a fugitive emissions inventory for site. It's basically an accounting. Dust that comes from roads, dust that comes from buildings, dust that comes from open mix areas. So specifically in this example, we're looking at road dust. And you find that when you look at the estimate, and it's a US Environmental Protection Agency method that we use, many of the others use exactly the same method, it's got a lot of variables that are built into it. So what goes into the estimate for lead emissions from a road includes traffic count, the vehicle weight, the distance traveled, how dusty the road is, the lead concentration, multiple variables go into it. And so we applied it for a specific example. In this example, our starting point is our copper products plant. And at our copper products plant, we transport what's called a lugger. So it's just a bin that holds lead sulfate material. The lead sulfate material is fairly wet. It's not going to dust out of that bin. So this is a traffic issue. This is the vehicle traveling. About 16 of those lugger trucks per day, up to that amount, travel from our copper products area down this stretch of road into our smelter recycling building. Okay, so 16 of those a day. This is probably the shortest distance that it can go from our copper products area into that particular building. But we looked at another option. In yellow is another route that we looked at, slightly longer, about 100 meters longer than the route we normally take. In terms of dust loading, this is a dirtier segment than the one we were looking at. The lead concentration about the same, but what really sticks out in this example is vehicle traffic. So if we take 16 lugger trucks a day off this red segment, that's a significant amount of the daily traffic that travels over that road. It makes a huge difference. If we take 16 and we put it onto this segment, which I have personally counted 250 movements in a shift, that's a very small increase on a stretch of road that already has an awful lot of traffic. This is what the map showed. So we had a reduction by taking those 16 lugger trucks off of the segment and placing them here of 618 kilograms of lead per year. We had an increase due to the additional traffic of 201 kilograms lead per year on this segment. Overall, it was a net reduction. We would not anticipate there to be much change in terms of lead concentration or dustiness of the road because these segments are influenced by other means. This is basically traffic. So this is a traffic scenario. And I'll show you the other thing. This is a picture of what that lugger trucks looks like. And what I didn't mention is an additional control we benefit by moving to this segment. We've got a bank of sprinklers that are used from mid-April to mid-October on that segment. An additional control in terms of controlling dust. So win-win in terms of accounting, win-win in terms of additional control. We made that move. And finally, monitoring is what informs what we do with fugitive dust. Monitoring on site for sources, monitoring off-site at our key community monitoring stations in order to show impact. So monitoring is really critical. Having your monitoring stations sited properly and getting the best information that you can get, really important. So what we've done is we've actually moved a station that's at Warfield to Haley Park location. We did that according to requests from BC Environment for siting purposes. So in order to meet siting, you need to sample all 4 quadrants that are around you in terms of airflow. You need to have a certain separation from structures. A lot of different things go into that. So siting was a big part of doing that. We're also looking at proximity to Webster School because we measure sulfur dioxide gas at our monitoring station. We're even closer to Webster School, so human health aspects definitely considered. And we'll see what it looks like. This is our current Warfield monitoring station. So the station in here where we have our sulfur dioxide gas analyzer. Up here we've got a high vol sampler that measures PM10. So it's dust that's less than 10 microns in size. It's got a dust fall, and over to the side there's actually a weather tower that's 60 feet in height. Very spread out footprint, but the key thing is look at the vegetation. So it's smothered by vegetation. Its access to airflow coming around it, it's not that great. So obviously BC Environment saying, can you move it somewhere else? And certainly we had to go through the steps of socializing that change because we put it at Haley Park, a recreational area. And what we did is we put in a really professional build. So we maximized the use of this space. We've got our sampler on the rooftop as opposed to spread out. We've got a crank down tower that we can service right from that platform. So it cranks right down and we can change out the sensor, etc. But right beside the platform, really nice footprint, really nice construction. And there's some future adds potentially in putting some recreationalization of the space, maybe some signage that's interactive for students that come from Webster School, learn about air monitoring, those kind of things. But a really professional build put there, meets the siting requirements, gives us really good quality data, builds into what we use globally for our air monitoring network to inform fugitive dust reduction initiatives.